Hello, this is Coach Travis, and what we got here is the third in a sequence of 3 videos showing how to use Riemann sums and calculus to find the exact area under a curve. So the curve that we're working with is 100 minus x squared, and we're trying to find the area under this curve between x is equal to 0 and x is equal to 8. And so what we did in the previous videos and what I have sitting up here at the top of the screen is this is the formula that if you tell me how many rectangles to use, then this formula will return the Riemann sum for that, the right hand Riemann sum for that number of rectangles. So for example, if n is 12, if you say to use 12 rectangles, if you put 12 into this formula, if wherever you see an n, you replace it by 12, then you will get basically 607.41, because it turns out that's what the area under all those rectangles is. But what if you change the number of rectangles? What if you want to use 22 rectangles? Well, okay, I promise you that if you put 22 into this formula for the number of rectangles in for n, then you will get about 617.52. You will get the exact area under those rectangles. In fact, this formula is even better than what the computer does, because the computer actually is rounding. The computer is only giving us an answer to 2 decimal places, but this will give us the exact answer. So this is giving us the exact area under all. If you add all the areas of these rectangles together, this is what you'll get when you set n equal to 22. So this formula, it's an amazing formula. It's magical. It's like, you know, again, the idea is if someone walked up to you on the street and said, all right, I want you to find the area, I want you to find the sum of the areas of all those rectangles. If I were you, I would say, well, okay, give me a couple hours and I'll do it. But with this formula, I can do it in a couple seconds. So this formula, we worked really hard to get this formula, but I think it was worth the work because this formula is extremely powerful. And now we're ready to use it to find the exact area under the curve. Because despite how awesome this formula is and how hard we worked for it, the thing we always have to remember is that the Riemann sum is not actually the area under the curve. The Riemann sum is just an approximation to the area under the curve. So the bad news is that this number 621.5, it's, as you can see, it's an underestimate. It's an underestimate to the area under the curve. But here's the punchline, and here's where the calculus comes in. The more rectangles we use, we can see the better our approximation will get. And if you can imagine, I mean, the way I program GeoGebra, it only goes up to 50. But if you imagine using 1 billion rectangles, if you imagine using billions of rectangles, you're basically going to get the exact area under this curve. You're not going to get the exact area, even if you use 1 billion rectangles. But you'll get so close that who cares? It's close enough. And so that's where the calculus comes in. And that's all we have to do now to get our final answer. All we have to do now is let the number of rectangles go to infinity. So that will be the actual area. So the actual area, let me show you a picture of it. The actual area under the curve, whoops, I need my pen. The actual area under the curve will be equal to the limit as n goes to infinity of our right-hand Riemann sum. So we've got this formula. This is the formula that if you tell me how many rectangles to use, then this formula tells you the area under all the rectangles. And we decided that, hey, if you could use infinitely many rectangles, then you'll get the exact area under the curve. So to finish this problem, all we have to do is just do the limit as n goes to infinity of this function. And this is actually, it's been a long time since we've done limits, but this actually is a really easy limit. The limit as I want the limit as n goes to infinity of 800 minus 256 over 3 multiplied by 2 plus 3 over n plus 1 over n squared. So I want to compute that limit. And this actually is thankfully a very easy limit. Because let's see, the 800, it doesn't care about n. The 256 over 3, it doesn't care about n. The 2, it doesn't care about n. Okay, but the 3 over n, it cares about n. Oh, but as n is going to infinity. So if you take 3 and you divide it by a really big number, then it's going to be getting close to 0. So as n goes to infinity, that guy is going to go to 0. And same thing with the 1 over n squared. Like 1 divided by a billion squared is practically 0. So that's going to be going to 0 as well. And so this limit is, let me write it down. Well, the 800, the limit, the 800 doesn't care about the limit. The 256 over 3 doesn't care about the limit. And the 2 doesn't care about the limit. And then everything else, the stuff that does care about the limit, it's turning into 0. And so we have our answer. We have 800 subtract, let's see, 256 times 2 is 512. 512 over 3. So my claim is, I'll go ahead and circle that. I claim that is the exact area under this curve. The exact area under this curve between 0 and 8, the shaded area in the picture is exactly equal to this. All right, and so let's just do a reality check here. So if I get out my calculator and I figure out what this is approximately 629. Well, it's not actually approximately. If the 3 repeats forever. So all right, so it's actually equal to that. So if I want to write it in decimal form, it's equal to that. And let's see what GeoGebra says. Does GeoGebra agree with us? If I ask GeoGebra to tell me what the area under the curve is, let's see what GeoGebra. All right, so yeah, so if I ask GeoGebra to tell me what the area under this curve is, it says 600. Look at that, 629.33. And that is exactly what we found doing this. And so, all right, so we did it. We've accomplished our goal. We can finally breathe a sigh of relief, and we have seen how we can use Riemann sums to end calculus, because we used a limit. And actually that's worth noting. Notice the calculus was the easy part. The calculus was the very final step. Everything we did before this, you didn't even really need calculus. So that's kind of cool too. And that just demonstrates the power of the limit, I guess. So anyway, so what are the takeaways from this? One, that was really hard. That took a really long time, and that was really hard. But again, it's like everything, the more you do it, the easier it gets. So this was the first time, this probably was the first time you've ever done this, and so it was really hard. But I promise you that if you do more and more examples, it'll get easier. It's always going to be a lengthy process. Getting to this formula is always going to take time, but at least you'll know what you're doing. The more you practice it, the easier it'll get, and the faster it'll get too. So all right, so let's pat yourself on the back if you made it through all of that, and it made sense. And if it didn't make sense, then go back and watch the videos again slowly and make note of the things that didn't make sense, and then ask me about them so that I can get you unstuck.